This section of the book is on inverse trigonometric functions. They're the final kind of basic functions that we're going to deal with, that most people deal with. Kind of the final transcendental functions that we have yet to look at. In a way, it should be extremely confusing to you, if you've never seen them before, that we even have inverse trig functions. To have inverse functions, to have an inverse function, the original function has to be 1-to-1. And trig functions are periodic. They're certainly not 1-to-1. The values repeat every pi or 2 pi. So they certainly don't have inverses. So what do we mean when we talk about inverse trig functions? So I've cheated. I have the graph of sine, a sketch of the graph of sine already on the board. This function is clearly not invertible. It fails a horizontal line test kind of spectacularly. Horizontal lines between 1 and -1 would hit the graph an infinite number of times because the function is periodic. So there's no way this has an inverse. So what do? We do what we did for the even powers. So x squared. X squared isn't 1-to-1. If you square a negative value and you square a positive value, square -2, square 2, you get 4. What did we do there to produce the square root? Well, you restrict the domain of your original function to an interval where the function is 1-to-1, and then you invert that restricted function. And that's what we do for all of the trig functions, although I said an interval, and for secant and cosecant we'll have to restrict to kind of pairs of intervals, but we'll see that in a minute. So here's the graph of sine. What do? We want to restrict the domain of sine to a region, to an interval on which sine is 1-to-1, and where sine takes on all of its possible values, so everywhere from -1 to 1. Well, there's an obvious nice region where that happens, between -pi/2 and pi/2. If you just look at this portion of the graph, between -pi/2 and pi/2, then that portion satisfies a horizontal line test. And so if we restrict the function sine to this interval from -pi/2 to pi/2, including those, that function will have an inverse. So strictly speaking, we're talking about a different function. And I go along with other sources here and actually give that function a different name. When I write sine, I always write a small s, but for the ordinary sine function, but I'll use a capital S sine to mean this one with the restricted domain, so that capital sine, it has domain -pi/2 to pi/2, and it has range and codomain, so -1 to 1. So you give it its domain, just we've artificially restricted the domain of sine to where its sine is 1-to-1. And so it's -pi/2 to pi/2, and the range you get every value between -1. This function has an inverse, and that's what inverse sine means. So, so you have this restricted sine function whose domain is -pi/2 to pi/2, and the range is -1 to 1. An inverse sine, which is typically just denoted sine inverse. It's this with this -1 to mean inverse. I remind you that that -1 does not mean 1/, it means the inverse function. Some people write arc sine, I will not, but sine inverse. It's the inverse function of this sine with a capital S, this restricted sign, but since there is no other inverse sign, you usually just see it with the little s, which is what I'll use. So this would be a function that goes, its domain will be -1 to 1, and its range will be -pi/2 to pi/2. in words, it's easy to say what inverse sine does. Inverse sine of some number v, what is it? Well, it's the inverse of the sine function, but the capital sine function. So it is an angle. So this is an angle whose sine is v, but there are an infinite number of angles like that. You give somebody a v between -1 and 1, there are an infinite number of angles whose sine is v. But it gives you back one between -π/2 and π/2, and there's only one of those. Angle whose sine, so let me call it angle theta, whose sine is v, such that theta is between -π/2 and π/2. All right, so that's what inverse sine is. It undoes sine in that particular region. I'll say this, I don't want it to be too confusing, but inverse sine of v, in particular, it's an angle whose sine is v. So if you take sine of inverse sine of v, all right, this is an angle whose sine is v, it has to be in a particular range of theta values, but so in particular, when you take sine of it, you get v. So for all v's in the domain of inverse sine, this equality is true. You have to be a little careful because it's simply not true that inverse sine of an angle, it is not necessarily true that this is theta again. Why not? Because inverse sine isn't really the inverse of this sine function. It's the inverse of the big sine function. If you start with an angle that's not between -π/2 and π/2, inverse sine can't possibly give that back to you. So it'll give you an angle between -π/2 and π/2 that has the same sign as the angle you started with, but it won't be the same angle if you pick your original theta to be outside the interval from -π/2 to π/2. So you have to be a little careful with these inverse trig functions. Aside from that, it's very manageable. We, of course, would like to know the derivative of this, the instantaneous rate of change of inverse sine. Well, we know that the sine of the inverse sine of x is x. And we know how to find derivatives of inverse functions. I was just going to say that we have a theorem that tells us that, in fact, inverse sine, because sine is differentiable, inverse sine will be differentiable except at the endpoints of this interval, because it's a closed interval, so you can't take limits on both sides. Inverse sine is differentiable, except at those endpoints. And so we can just use the chain rule, which is what the formula for the derivative of the inverse function gives you. So we know that the sine of the inverse sine of x is x for all x's between -1 and 1. And that includes at -1 and 1, but when we take derivatives, we'll leave those. We won't be including those because inverse sine is not differentiable there. So you take the derivative of both sides of this with respect to x and use the chain rule. The derivative of the outside function, derivative of sine is cosine. You leave the inside stuff the way it is, but then by the chain rule, you have to multiply times the derivative of inverse sine. And that has to be the derivative of x, which is just 1. So what we get is that the derivative of inverse sine of x is 1 over the cosine of the inverse sine of x. And you might think, well, that's kind of a nice formula, a little unattractive, but kind of nice. Well, it's nicer than you might think. This looks very trigonometric-y. You've got an inverse trig function, then you do another trig function. But in fact, when you combine those two, what you get is 1 over the square root of 1 minus x squared. Why is that? So I'm claiming that the cosine of the inverse sine of x is the square root of 1 minus x squared. Why is that? Well, let's look at it. So we want to kind of simplify, to get the algebraic expression, the square root of 1 minus x squared, for this thing. So what do? Well, let's let theta, so just let theta be the inverse sine of x. So this inside quantity. What does that mean? It means two things. It means first that sine of theta equals x. So sine of theta equals x. And it means that theta is in the range of inverse sine, which is the domain of that restricted sine function. So it also says that theta is between minus pi over 2 and pi over 2. All right, so what? Okay, we have the fundamental trig identity that sine squared plus cosine squared equals 1. So we know that the sine of theta squared plus the cosine of theta squared equals 1. Why am I interested in that? Oh, well, we called this inside thing theta. So this is just the cosine of this theta. And we'd like to know what it is. Oh, we'll solve this for cosine of theta. Cosine of theta, then, is plus or minus the square root of 1 minus sine squared theta. But sine of theta is just x. So sine of theta is just x. So this is plus or minus the square root of 1 minus x squared. Great. We'd be finished and have that this is the square root of 1 minus x squared if we knew we had the plus sign and not the minus sign. How do we know? It's the restriction on theta. Theta is between minus pi over 2 and pi over 2. Cosine of an angle between minus pi over 2 and pi over 2. Think the x-coordinate on the unit circle between minus pi over 2 and pi over 2. That's greater than or equal to 0. So we get the plus sign because theta has to be in this range. And so you get this, which gives us this formula for the derivative of inverse sine. It is 1 over the square root of 1 minus x squared. This is actually very cool. You have this thing that's defined in terms of trig functions and their inverses, and you take the derivative and you see no hint. You see absolutely no hint of a trig function in the derivative. This does mean that you could actually define inverse sine in terms of anti-differentiating this function. And so that would give you a definition of inverse sine that in no way refers to circles or anything that looks trigonometric, and then you could be very bizarre and use that definition of inverse sine to define sine, and anyway. We won't do that, but you could. All right, this is the derivative of inverse sine. We've defined inverse sine, we've found a formula for its derivative. We need to do the same thing for the other 5 trig functions. So I won't derive all of the differentiation formulas, but I do need to tell you how you restrict all the functions. So, and secant and cosecant are certainly the worst. Okay, let's look at cosine. So we know the graph of cosine. It roughly looks like this. Again, we want to pick kind of a fundamental domain for cosine, an interval on which cosine is 1 to 1 and where cosine takes on all of its possible values between +1 and -1. Well, there's an obvious one. Well, it would be more obvious if I would put numbers on here is pi. There's where x is pi. We're going to pick this part of the graph right here, where the function, where cosine takes on all its possible values. So all the values between -1 and 1, and does it exactly once. So that this part of the graph passes a horizontal line test. This restricted function is 1 to 1 and on to. So cosine with a big C means the function with the restricted domain 0 to pi. And that maps onto the closed interval from -1 to 1. I should have emphasized this a minute ago. I said that the function inverse sine would not be differentiable at the endpoints when x is -1 and 1 because we're on a closed interval. It's not like you have to remember that as something special. If you tried to put -1 or 1 in for x here, you'd get division by 0, so the expression would be undefined. So it's the formula itself tells you that things are bad at plus or -1. All right, here's inverse cosine. Here's cosine. Inverse cosine is the inverse of this function. So inverse cosine. Inverse cosine. Its domain, set of numbers from -1 to 1, including -1 to 1. It gives you back angles between 0 and pi. In words, you should be able to say what inverse cosine is. The inverse cosine of v. It's an angle whose cosine is v, but it's the unique angle between 0 and pi, including 0 and pi, whose cosine is v. Okay, so that's inverse cosine. What's its derivative? Well, you do something just like this. Here's cosine, inverse cosine. You differentiate both sides with respect to x and apply the chain rule. You get minus the sine of the inverse cosine of x times the times the derivative of the inside function. So times the derivative of inverse cosine of x, and this equals 1. You divide both sides by this, you get derivative of inverse cosine of x is -1 over the sine of the inverse cosine of x. And just like the cosine of the inverse sine, you see that this denominator is the square root of 1 minus x squared, but you have this minus. So, in fact, you get that the derivative of the inverse cosine of x is negative 1 minus x squared. Okay, I'll leave it to you to verify that it works out the same. I mean, the denominator gives you the square root of 1 minus x squared, but you get the minus sign. That's our formula for the derivative of inverse cosine. We need inverse tangent, inverse cotangent, inverse secant, and inverse cosecant. Let me kind of do tangent and cotangent side by side. At least there are restrictions, and give you derive one of the derivative formulas for you and let you do the other one. You should recall that tangent and cotangent are pi periodic. Their period is pi, not 2 pi. And their graphs look, this is roughly the graph of tangent. And it does the same thing over here. All right. Well, it's pretty obvious Oh, I said I was going to do sine and cosine, tangent and cotangent, side by side. So let me. Cotangent looks, well, I will do it side by side, but let me say this first. What's an obvious choice of a restricted domain for tangent where we'll get a one-to-one function that has an inverse? Well, there's an obvious chunk, just the piece in between asymptotes. And yeah, this one that passes through the origin certainly is an obvious choice, and that is the choice we make. So we look at this part. So the restricted tan function, so with a capital T, which I've drawn kind of a fancy way, the restricted tan function, it goes from the open interval from minus pi over 2 to pi over 2, right? You can't include the asymptotes, into, well, the entire, you get every real number back from tangent. So from minus infinity to infinity. And what do we do for cotangent? Well, I won't draw the repeated part, but you should remember the graph of cotangent kind of looks like the graph of tangent, only kind of shifted and reversed. The graph of cotangent looks like this, and this repeats. And so, yeah, we pick for cotangent, for its fundamental domain, we pick this part from 0 to pi, where you can't include 0 and pi. So our big cotangent, our restricted cotangent, it will have domain minus, no, we'll have domain 0 to pi, and it also has range minus infinity to infinity. And so we invert these functions, and we get inverse tangent and inverse cotangent, which are, give back angles. So inverse tan of v gives you back an angle, whose tangent is v, but it gives you back an angle between minus pi over 2 and pi over 2. Not just an arbitrary angle, whose tan is v. So we've got inverse tan. Inverse tan, you can give it any real number, and it gives you back an angle between minus pi over 2 and pi over 2. And there's inverse cotangent. It's from minus infinity to infinity and gives you back an angle between 0 and pi. And there are things you can tell from the graph. For instance, as x approaches pi over 2 from the left, tangent approaches positive infinity. What does that mean? It means as you take the limit of inverse tan of v, as v approaches infinity, you get pi over 2. So you can just read properties of inverse tangent and inverse cotangent from the fact that they're inverse functions, and look at the graphs. The derivatives are not so easy just to look at the graph and spot. So let's look at the derivative of tangent. So what do? Or inverse tangent. You write that tan of inverse tan of x is certainly x. We're assuming inverse tan is differentiable because we have a theorem that tells us that it is. So you apply the chain rule on both sides. Derivative of tangent. Oh, the derivative of tangent is secant squared. And then you have that done to the inverse tan of x times the derivative of the inverse tan of x equals 1. So you get that the inverse tan of x is 1 over secant squared of the inverse tangent of x. And as before, okay, this isn't that bad a formula, but looks like you definitely get trig functions involved. But as before, because you have an inverse trig function and a trig function done to that, you would hope that it would simplify or turn out to be some nice algebraic expression. And it does. That is just 1 plus x squared. There's no square root this time. Why is that? You just work it out. So probably our second most important trig identity, I'll remind you that tan squared theta plus 1 equals secant squared theta. That one. So what do we get? We've got that, yes, what do we have? We have a mistake because this was supposed to be the derivative of inverse tangent and I didn't write the derivative. That's okay, that looks better. So we have that the derivative of inverse tan of x equals 1 over secant squared inverse tan of x. And we'd like to see that that denominator is 1 plus x squared. So what do? You call this part theta, or call it anything other than x. X would be a bad choice. Call it theta, so that the tan of theta is x. But then we have this fundamental, or second fundamental, we have this basic trig identity that tan squared plus 1 is secant squared, but tan of theta is x. So this says x squared plus 1 is secant squared theta. But secant squared theta is exactly what we've got. This is theta, there's secant squared theta. So it's 1 plus x squared plus 1. So yes, we get this formula for the derivative of the inverse tangent, that it's 1 over 1 plus x squared. I will leave it to you to verify that working in the same way, you find that the derivative of inverse cotangent of x is negative 1 over 1 plus x squared. Right, so it's negative what you get for the derivative of inverse tangent. You may notice, let's see, the derivative of inverse sine, 1 over the square root of 1 minus x squared. The derivative of inverse cosine, so the derivative of the inverse co-function to sine, is negative 1 over the square root of 1 minus x squared. So their derivatives are just different by multiplication by minus 1, and they're co-functions. The same thing happens with tangent and cotangent. The derivative of inverse tan of x is 1 over 1 plus x squared. The derivative of inverse cotangent, so the co-function of tangent, is just negative what you got for the derivative of inverse tangent. The same thing will happen with inverse secant and inverse cosecant. So let's go ahead and look at what you get for those. I'm going to go ahead and tell you what you get. These are the most complicated ones, and it's because, well, they're the most complicated functions to define because the domains are so messed up before you invert. I should warn you, so we will find that the derivative of inverse secant is 1 over the absolute value of x times the square root of x squared minus 1. And the derivative of inverse cosecant, as promised, will be negative that. All right. I should warn you that different books actually make different choices for the domain of inverse. Well, they make different choices for the restricted domain of secant and cosecant than we're going to make. And it actually changes the derivative formula. The question is whether you have these absolute value signs here or not. The choice we're about to make is the more common one. But you need to be careful when you're reading about any formula involving inverse secant and inverse cosecant. You have to know how that source has defined those. what a lot of people do is just try to avoid using inverse secant and inverse cosecant. Do any problem involving trig and inverse trig functions. Use inverse tangent or inverse sine or inverse cosine. Avoid these. I won't do that, but I just need to warn you that different people make different choices here. All right. So let's look at y equals secant of x. I remind you that that is 1 over cosine. And so it has the same kind of asymptotes as tangent, which has cosine in the denominator. So pi over 2 minus pi over 2, 3 pi over 2 minus 3 pi over 2. So you've got these asymptotes. And the graph of inverse secant, here's 1, here's, well, let me draw that a little closer. Here's 1, here's minus 1. What's the graph of secant? Well, in here, you get, secant always has values either greater than or equal to 1 or less than or equal to minus 1. So in there it's that. In this region, it's this. And then this starts repeating. So in here it would be this, and over here it would be this. All right. So if we want to take a region, restrict the domain of secant in such a way that we get a one-to-one function that takes on every value that secant takes on. Well, the values that secant takes on, it's all the numbers greater than or equal to 1 and all the numbers less than or equal to minus 1. We can get the ones that are 1 and bigger by taking this part of the graph. Unfortunately, we can't take this other part, though that just gives us the values between 1 and infinity again, and that graph wouldn't, that function wouldn't be 1 to 1 because the graph wouldn't pass a horizontal line test. So where do we get values between minus 1 and infinity? Well, the obvious choices are to take from here to here or from here to here. It's a choice. Do you take this closest interval between pi over 2 and pi, or do you take this one over here that, well, anyway, we're going to take this part of the graph. Certainly this function, if we restrict the domain, we get a one-to-one function. This is not an interval anymore. There are two intervals. There's an interval from 0 to pi over 2, and then pi over 2 to pi, but there's this break because you can't, pi over 2 itself is not in the domain. So we restrict the domain of secant, and we get big secant. Big secant goes from, well, it's a little unattractive. It goes from, you give it values between 0 and pi over 2. You can include 0. You can't include pi over 2. Or you can give it, that's a union symbol. It means the union of the two sets. It's all the x's that are in this one together with all the x's in the other one. Or x is between pi over 2 and pi. And you can include pi. So this is a kind of fancy way of writing that x is in the interval from 0, the closed interval from 0 to pi, and x is unequal to pi over 2. So that's the domain of secant. Its range is also a little annoying. You can get anything between minus infinity and minus 1, including minus 1, or you can get things that are 1 or greater. So it's a union also. So this is a fancy way of saying that the y values you get out, you need something greater than or equal to 1 or less than or equal to minus 1. All right. So that's what this big restricted secant is. Its domain is this set that's the union of two intervals. Its range is this set that's the union of two intervals. So inverse secant is really fairly unattractive. It's so inverse secant goes from minus infinity to minus 1, so its domain is this set, and its range is the domain of the restricted secant, so it's the 0 to pi over 2 union pi over 2 to pi. Awful. You can see why people might want to try to avoid this. And what do you get for the derivative of this? All right. So we do what we've been doing. You take secant of inverse secant of x, and that will be x. You differentiate. The theorem does tell us that this will be differentiable except at the endpoints of these intervals. You can just apply it to the two pieces of the interval separately. So what we're doing is fair. You differentiate both sides. You use the chain rule over here. The derivative of secant is secant times tangent, and you leave the inside stuff alone. So we'll get the secant of inverse secant of x times the tangent of the inverse tangent of x. That's the derivative of the outside function, leaving the, tangent of the inverse secant of x. You leave the inside stuff how it was. But then, by the chain rule, you have to multiply times the derivative, the inverse of the inside stuff. And this will equal 1. So we get the initial formula that we'd like to write in algebraic terms, that the derivative of inverse secant of x is 1 over this stuff. All right. Well, at least secant of inverse secant, that's just x. So that's fine. So we get x, that part. And then you divide by tangent of inverse secant of x. So this is what we actually get for the formula. But we'd like to make the tangent of the inverse secant of x algebraic. And so we do. Okay. What do you do? The tangent of the inverse secant of x. Well, as you would suspect at this point, we call this theta, so that we're after the tan of theta. And what we know is that, well, theta is this inverse secant, so the secant of theta is x. But we also know that theta has to be in the range of inverse secant. So theta has to be in here. So we know that theta has to be between 0 and pi, and theta is unequal to 2 pi, pi over 2. All right, great. So what do you get? Well, you use that tan squared theta plus 1 equals secant squared theta, which means subtract 1 from both sides, take square roots, you get a plus or minus. So tan theta is plus or minus the square root of secant squared theta minus 1, but secant theta is x, so this is plus or minus the square root of x squared minus 1. Good, so what we get is that this is 1 over plus or minus x times the square root of x squared minus 1. But my formula that I had the absolute value of x here. Now it's true that the absolute value of x is plus or minus x, but the absolute value of x is x when x is positive, and negative x if x is negative. Because if x is negative, like negative 2, its absolute value is 2, which is negative what x is, negative, negative 2. So it's not just kind of a random plus or minus here, or unknown. You actually need the absolute value of x, and so we have to be a little careful to see when we get this. So what happens? Well, if x is negative, then you're in this interval. So if we, right, this is the domain of inverse secant. If x is negative, you're in this interval between minus infinity and minus 1. That's exactly the part, I've erased the graph, but that's exactly the part of the graph that gives you back angles in here, right? So if x is negative, theta, so what I'm saying is if x is negative, theta is in, well, I'll just write it as theta is between pi over 2 and pi. On the other hand, if x is greater than 0, then theta is between 0 and pi over 2. Okay. And then you look at tangent. When theta is between pi over 2 and pi, so picture the graph of tangent. When theta is between pi over 2, or look at the signs of sine and cosine. When theta is between pi over 2 and pi, so maybe it's just easier for me to say it in terms of sine and cosine, then the tangent, the sine of an angle between pi over 2 and pi is greater than or equal to 0, but the cosine is negative, so tangent is negative. So theta's in here. If theta's in here, then tan of theta is less than or equal to 0. And if theta is between 0 and pi over 2, this is where tan of theta is greater than or equal to 0. All right. That means you pick the plus sign here. So, right, tan of theta is positive. You pick the plus sign exactly when x was positive. So we get the plus sign when x is positive. We get the minus sign exactly when x is negative. Okay. What does that say? It says if x is positive, we pick plus, so we still get positive. If x is negative, we pick minus, but then negative x is a positive number. That's why we get the absolute value of x here. I will leave it to you to verify. Well, we need to define inverse cosecant. It too will have this domain. I'll give you its range. I'll draw the picture so that you can figure out its range. But yeah, the two formulas that we get, they're negatives of each other. We get the derivative of inverse secant of x is 1 over the absolute value of x times the square root of x squared minus 1. And we get the derivative of inverse cosecant is negative that. I, of course, need to tell you where you restrict cosecant. You should really be able to figure this out. Cosecant is 1 over sine, so it has asymptotes where sine has asymptotes. So sorry, it has asymptotes. Yeah, it has asymptotes where sine is 0. So cosecant of x is 1 over the sine of x. Every place that sine is 0, you'll have an asymptote. Well, that's it. 0, and then at pi. And then, of course, it repeats. So you have asymptotes at 0 and at pi and at 2 pi and at minus pi, minus 2 pi. And again, all the values are either greater than or equal to 1 or less than or equal to minus 1. And what do you get in between? What do you get in between the asymptotes? Well, you get exactly what looks like the graph of. It looks just like the graph of secant, except shifted over. So. And then this repeats. So. Okay. So we want to take a region in which this is positive, where it takes on all of its values, and where the function is 1-to-1. So what do we pick? Well, there are a number of choices, possible choices, but we're going to take this region. Right? So that function is now, the restricted function is 1-to-1. So we have this, let me just write. Our inverse cosecant, its range will be, you get angles between minus pi over 2, minus pi over 2 and 0, union 0 to pi over 2. All right. Those are the inverse trig functions. They are, you have to restrict the domains of the ordinary trig functions and invert them. Inverse secant and inverse cosecant are certainly the worst. I want to do some examples. We have the derivatives. I want to do a few examples, and then we'll leave these. If inverse secant and inverse cosecant look extraordinarily ugly to you, they are. And seriously, people try to avoid using them, not just because they're ugly, but because their ugliness has led to different people picking different definitions of them, which just differ by what restricted domain you use, but those differences actually change the formulas for the derivatives. So if you want to avoid inverse secant, inverse cosecant, you can probably do it in every physical problem. All right, but let's look at a couple of examples of, now that we have the derivative formulas, we have the inverse functions and the derivatives, let's just do a few examples to just calculate some derivatives in one word problem. So let's look at z equals the inverse tangent of, I want e to the v. So this is an example. So what's dz dv? The derivative of z with respect to v? Well, you just combine this with our other combine our new derivative formulas with our old ones. And so we have one function done to another function. You use the chain rule. So you differentiate the outside function. So take the derivative of inverse tangent. You leave the inside stuff exactly how it was. But then by the chain rule, you would have to multiply times the derivative of the inside function. The derivative of e to the v with respect to v, just e to the v back again. But the derivative of inverse tangent, the derivative of inverse tangent of x, 1 over 1 plus x squared. And we've got 1 over 1 plus e to the v squared times e to the v. And so we end up with e to the v over 1 plus, when you raise something to an exponent, the exponents multiply. So you get plus e to the 2v. That's it. That's what you get. All right. What's another example? Oh, how about we use one of our inverse secant or inverse cosecant formulas. So let's look at w equals r inverse secant of r. What's dw dr? So the derivative of w with respect to r. This is the product of two functions of r and the inverse secant of r. So use the product rule. It's the first thing times the derivative of the second plus the second thing, the inverse secant of r, times the derivative of the first. And now you have to remember the derivative of inverse secant, which is the absolute value of r times the square root of r squared minus 1. That r comes from that r. And then plus, the derivative of r is just r. So plus the inverse secant. The derivative of r is just 1. So you get plus the inverse secant of r. You get this. If r is positive, then r divided the absolute value of r would just be r. So you could cancel these. If r is negative, then this would be negative r, and this would be negative 1. So this part, you could write it in cases as this is 1 over the square root of r squared plus minus 1, if r is positive. And by the way, that's if r is positive, right? Oh, but what if r is plus or minus 1? So r is positive. What if r is 1? We're taking inverse secant, and we're taking its derivative, and it won't be differentiable when r is 1. So this is really if r is greater than 1, and then it's minus 1 over the square root of r squared minus 1 if r is less than minus 1. So, all right. Those are easy examples using our new differentiation formulas. Let's do one word problem before we stop. So kind of in the last section where we had tangent, or where we first looked at the derivative of tangent, we had a lighthouse problem and a girl running along the beach trying to keep up with the light. Let's do kind of, we were given the rate at which the light in the lighthouse was rotating and ask how fast the girl was running. Let's do the reverse problem since it will use inverse trig functions. So what do I mean by the reverse problem? So now, let's suppose this is a wall, a top view of a wall. We're looking at some kind of prison yard, and here's some guard tower. So guardhouse, guard tower, guard tower. And let's say this is, I want to use the same numbers as in the book, 150 feet. So this is a fixed distance to the wall, 150 feet, call this point P. And now what's happening is some prisoner in the prison is running right beside the wall. So this prisoner is running. So call the distance from this closest point on the wall to the guard tower. So this point P is the closest point on the wall to the guard tower. Call the distance between that point and the prisoner X. I'm going to assume the prisoner is running at 15 miles an hour. Which is 22 feet per second. And then he's running to the right from our top view. Actually, it's a top view of all this setup, except it's not a top view of the person, because that would just look like I don't know what it would look like. Anyway. Guardhouse, there's a spotlight in it. And they are trying to keep the spotlight on the prisoner at all times. And so there's some angle theta here that the spotlight beam makes with this ray that goes, or maybe another wall, that goes from the guard tower to the point P. And the question is, how fast, at what rate must the spotlight be turning? So at what rate must the spotlight turn when the prisoner is, I think, 50 feet. Yep. When the prisoner is 50 feet to the right of the point P. At 22 feet per second to the right. All right. So, what do? Well, it's a trig problem, some kind of trig problem. We need to write an equation that relates x and theta. Why? Because this, the prisoner's running at 22 feet per second, is dx dt. We are told that dx dt at all times, dx dt is 22 feet per second. That is what we're given. We're asked how fast is theta changing as a function of time. So we need some relation between theta and x that's true at all times at the interval that we're interested in. So what do? Well, trig functions. You can use tangent. The tan of theta is the opposite side over the adjacent. This adjacent side is 150 feet. So we get that the tan of theta, at all times that we care about, tan of theta is x divided by 150. That's at all times. But now we can take inverse tangent. Certainly the angle theta that we care about is between 0 and pi over 2, so that it's in the range of inverse tangent. So tan theta equals this, which means that theta, as long as theta is between minus pi over 2 and pi over 2, which it is, that theta has to be the inverse tangent of x over 150. Okay? And we're after d theta dt. Exactly what we're asked for. The rate at which the spotlight is rotating. D theta dt when x is 50 feet. This is what we're asked for. Great. Differentiate both sides with respect to time. And this is a function of time. You just have to use the chain rule. So d theta dt. The derivative of inverse tangent, 1 over 1 plus, normally x squared, but now it's this quantity squared. X over 150 squared. But by the chain rule, you have to multiply times the derivative of the stuff inside with respect to t. Right? We're differentiating with respect to t on both sides. So you get this, but then you have to multiply times the derivative with respect to t of this part. Oh, but that's just 1 over 150 times dx dt. But we're given dx dt, it's 22 feet per second. So we get 1 over 1 plus x over 150 squared times 1 over 150 times dx dt. And so the d theta dt that we're after, I don't need my picture anymore. We're after d theta dt, the rate at which that angle was changing. D theta dt, but we only care when x is 50. I'm going to drop the units. This will be in radians per second. D theta dt, we get, when x is 50, what we just found is we get 1 over 1 plus, it was x over 150 squared, but we only care about this when x is 50, so it's 50 over 150 squared times the 1 over 150 times dx dt, which is 22. Right? All of this will come out in radians per second. So what do we get? Well, this is just a third squared, so this is 1 over 1 plus a ninth times, well, 2250ths, you can write that, is 11/75. This is 9 ninths plus 1 ninth, that's 10 ninths. 1 over 10 ninths, 9 tenths. So we get 9 tenths of 11/75, so we get 99 over 750, which is approximately 0.132 radians per second. So that's how fast they're having to turn the light to keep up with the prisoner when the prisoner is 50 feet away. You might wonder if that's ridiculously fast. Pi over 4 radians is 45 degrees, and pi over 4 is about 3/4, so it's about 0.75. This is much slower than that. So they're not even having to turn it 45 degrees a second, which would be easy to do. So they're not having to turn it that fast to keep up with the prisoner. They're having to turn it relatively slowly. All right. I think that's enough on inverse trig functions. They come up in lots of settings. They're our last set of functions that we needed to define and find the derivatives of. There's one more section in this chapter. It's on implicit differentiation, where we don't look at new functions exactly, except we look at functions that are kind of defined implicitly by equations. So, I mean, they are new functions, but not explicitly. Anyway, we'll look at that in the next section.